So these cells, they can live alone. We do not have to have them dependent on each other. You do have single cell organisms. You do also have complex organisms like us. And they are going to possess this unique genetic material. This genetic material is known as DNA, and it is the blueprint. It is the job description for what the cell is supposed to do. How is it supposed to act? And what exactly is its basic function in life? So our multicellular organisms like us, like dogs, like cats, we have all of these cells that are grouped together in this specialized tissue. And then that specialized tissue works with other specialized tissue in order to make us be alive. In my liver tissue, although does a different job than my kidney tissue, I need both in order to sustain my life. So as we start talking about more and more complex organs, more and more complex systems, the first thing we do have to understand is, how do the cells work? This is the basic idea behind physiology. Remember, anatomy is the structure. Physiology is how does it work? And so the cell is the most basic unit of how does all of this stuff work. I'll give you guys a minute. I know that you guys are doing bones. You guys have already had midterm, right? Yeah, because I'm actually teaching the other group midterm now. So I know exactly what you guys are studying. Need some bones over here, so I'll know how to quiz you. This is my favorite bone. Anyone have a guess what this is? Yeah, it's a pelvis. It's the pelvis of a cow. It's also the world's greatest Mardi Gras mask. And this is where the babies come out. All right, so let's talk a little bit about evolution and what happened with our cells, because some really interesting stuff happened. We have these primitive cells. We think that they resembled what bacteria looks like today. Let's see if I can move these guys over. So we have these very primitive cells, and these primitive cells are called prokaryotes. Pro meaning what? Before. Karyote means nucleus. These prokaryotes were single-celled organisms. They did not contain a nucleus. They did, however, have genetic material. It just wasn't contained in this nuclear envelope. It was just kind of free-floating around inside the being. And then what happened is cells started to evolve. Now, in my mind, these cells are having a little conversation with each other. Obviously, that's not exactly the way it happened. But we ended up starting to see these eukaryotes, eu meaning good, karyote meaning nucleus. And so these cells are getting more and more complex. And what's happening is, essentially, in evolution, the prokaryote is like, hey, check out fancy guy over there. See, you're getting pretty complex. So you got a whole other area for your DNA. That's pretty fancy. He's looking down at himself and he's like, I don't feel very fancy at all. And he's like, hey, complex cell, I got a proposition for you. Complex cell is like, okay, well, I'm just over here evolving. Let's talk. Prokaryote goes, hey, looks like you're using a whole heck of a lot of energy. Where are you getting all that energy? And the cell is like, I don't know. I'm kind of struggling with that one. Prokaryote goes, okay, I got a deal for you, man. You give me a safe place to hang. You give me a crash pad. You let me kind of come and, stay inside you. I will provide you with the energy you need to function. Complex eukaryote is like, heck yeah, that sounds amazing. Come on over. And prokaryote, comes over and gets engulfed and becomes part of the more complex cell. This is now what we know as the mitochondria. Now, why do we think this is the way it happened? Because mitochondria has its own DNA. just like the prokaryote. The other thing about the mitochondria is it does live up to its name. It does live up to the deal that prokaryote made with the more complex cell. When my eukaryote decides that it needs more energy, it just doesn't have enough to do the job at hand, mitochondria is able to go and make another one. And he can just keep replicating himself to give that energy boost that the cell needs to do whatever complex job it's meant to do. So that's why we think that that's kind of how these cells evolved from these non-nucleus cells to the more complex cells that we see that make us up today. Got a couple of pictures coming up here. Give you guys a minute. All right, here we have some pictures. Here I have the prokaryotic cell before nucleus. See, I do have my DNA, but it's not contained within the nucleus. Next to it is my eukaryotic cell, meaning it does contain a nucleus. You can see right here, and that's where my DNA is. Now let me give you a size comparison because I know this picture makes it look like this cell and that cell are the same size. They are not. My prokaryotic cell is much, much smaller. This turned into this. This is the mitochondria of our complex cell. So that's the size difference that we're looking at. These prokaryotes are way, 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 way smaller, and they are able to fit inside that eukaryotic cell and give it the energy it needs to conduct whatever complex function it's supposed to do. That's it. Why are cells so small? Well, it has to do with the energy and the nutrients needed to keep them alive and keep them working. When I have tiny cells, they're able to feed themselves much more efficiently. They're able to absorb nutrients, they're able to excrete toxins, and it's far more efficient than if they were ginormous. The other thing is with smaller cells is that they can be governed by a single brain. They can be governed by a single nucleus. Now that's not to say we don't have some cells in our body that are humongous, like muscle cells are humongous in comparison. Nerve cells can be humongous. The larger the cell, the more brains I need to make it work. So I could have a single cell with multiple nucleus, because the bigger the cell I now need, if we think about now the nucleus does more stuff than just a brain. But if we're gonna just go down to super basics, the nucleus functions like the brain of the cell. If I have a humongous cell, I need more brains to make it go. So I can have multi-nucleated cells. But that's the reason why cells are so small. Because if they were ginormous, if they were the size of a rock or a boulder, excuse me, I simply couldn't have enough nutrients to make it work. I couldn't feed it the oxygen. I wouldn't be able to pick up the toxins, but I'd also need more brain power than what I am capable of giving it. So that's why cells are so insanely small. Now, again, we have some cells that are larger than others, and the number of brains that they use will be determined by the size and the function. So like our skeletal muscle, as I said, are multi-nucleated. Our cardiac muscle, multi-nucleated. Holy smokes, our cardiac muscles are so insanely complex because not only do they have to contract at the exact same time, at the exact same rate, and at the exact same strength, that is all got to be coordinated. Otherwise, if we have some cells that are contracting and other cells that are like, I don't want to right now, we end up with a heart that is not pumping coordinated. We end up with something that looks like this. That is not a good thing for the heart to be doing. So that's just an example of how these multinucleuses, nuclei, nucleuses? No, it's nuclei. Thank you. I was like, that doesn't sound right. Nuclei are going to help coordinate the function of these cells. Now, both plants and animals contain cells. We are going to function most on the mammal cell. The mammal cell, all mammal cells, contain some similar structures. We have the cell membrane, which functions very similar to my skin. In fact, I think of it like the skin of the cell. This cell membrane, this skin, helps keep stuff in and keep stuff out, right? My skin keeps all of my internal organs on the inside of my body, but it also separates me from the environment. But it also allows certain selective things to pass back and forth through it. That's exactly what's happening with our cell membrane. It helps to keep all of the cell guts on the inside, separates it from the environment, and regulates what is moving in and out of the cell. Inside the cell, everything, the guts, the organs, the blood. Now, obviously, do cells have organs and blood? Well, kinda. That's all known as the cytoplasm. So everything on the inside of the cell is the cytoplasm, and it is separated from the environment by the cell membrane. Finally, we have the nucleus. This is the brain of the cell. It contains all the genetic material. So those are the basic common features of all of our mammal cells. It does not matter if you are a cow, a goat, a dog, a cat, a person. All of these features are going to be the same. They might look slightly different, they may function slightly different, but ultimately this is what makes up a mammal cell. Everybody okay? We're going too fast, too slow? Everybody's bueno? Fantastic. The other reason why I think of cells as little people is because they really do have all the same things. They have organs. They have what are called organelles. We're going to talk about these in detail here in just a sec. Organelle just means tiny organ. I got some organelles in my cell that function like kidneys. I've got some that function like a stomach. I have one that functions like a brain. I also have a skeleton. My cells have a skeleton of their very own. Now, obviously, it's not made of ossified material like this, not per se, but it does the same function. It helps to keep the cell stable. It helps have attachment points for things in the cell. It helps things maneuver and be transported around the cell. It's called the cytoskeleton, and it does function just like our skeleton in our own bodies. If you break the cytoskeleton, it can repair itself to a degree, right? Like if you break a bone, you can have it heal, but if you break every bone, now you're going to probably have a much worse day. And just out of curiosity, since I know you guys are doing bones, how many people in here have broken a bone at some point in their life? What did you break?
I broke in a bunch of fingers.
Ooh.
And then I broke my forearm.
Oh my goodness gracious. Who else has broken a bone? What'd you break?
I broke my fourth metatarsal in my foot, actually working out of pain.
Oh my goodness.
Yeah.
So
I was walking downhill and I just had to pull down my ball.
oh, and that's a tough break to heal
Yeah.
because you are weight bearing on it.
Mm-hmm.
Anybody else? Nobody else has broken a bone.
I broke my pinky toe and my rumbles on the side of your foot right here.
Ooh.
I remember because of my brother.
Yeah. your body was able to mend, your body with some medical intervention. But just like our cytoskeleton, that damage was very apparent. You get a big bruise, right? Breaks, oh my goodness, if you break a bone, holy smokes, does it bruise. Worst bruise I ever had was when I broke my ankle. I broke my knob. Let me clarify that because that didn't come out right. I broke my inside ankle knob. So if you look at your ankle, stop up here. If you look at your ankle, I actually no longer have a knob. Look how weird that is. I don't have a knob on the inside of this ankle. I got a knob on the outside. I don't have a knob on the inside because I sheared it off. I was lifting up a sample of some tile that I was looking at from my floor. And so it was really big and heavy. And I was holding it up like this to try and lift it, and I dropped it. And it came down and sheared my knob. And it never grew back properly. It never healed properly. So, same thing with our cytoskeleton. It can heal incompletely, but you're still going to have some healing properties. Yeah, I also fractured my skull. It's really hard to fracture your skull. That was not a good day. Here's a cross section of an animal cell. Anybody who's ever taken any high school biology class, you've seen something similar to this. You've seen something similar. You've probably even heard some of these terms. Here we've got our nucleus. Extension of our nucleus here is the rough ER. Can anyone tell me what ER might stand for? Our endoplasmic reticulum. Does anyone know what these little purple dots are that are making it look rough? Those are our ribosomes. Those, remember, are the factories. We transition here to the smooth ER. Here we have the Golgi body. This is the FedEx store of our cell. This is where we send stuff to be repackaged, put a FedEx label on it, and get transported around or out of the cell. Here I've got my vacuole. This is like the digestive system of my cell. This has gastric enzymes that are going to help to dissolve things. Here I have the fluid, which is my cytoplasm. Here's my mitochondria, my little energy producers. My lysosome, my centrosome. These are kind of our suicide part of the cell. It's when the cell is ready to give up the ghost and it's no longer being a contributing member of society. It turns this on, it kills the cell. So these are all of the parts that we're going to talk about in a little bit greater detail. So let's talk a little bit about the skin of our cell membrane. Now there is a video on my website that you can watch called The Cell Membrane. It's a great video by Bozeman Academy. I do recommend that you watch it because it kind of puts all of this into some different terms. I also have one about the cytoskeleton. So basically what the cell membrane is just like our skin. As I said, it is flexible. It can heal itself to a degree. I mean, if I get a little paper cut, that's going to heal, no problem. If you peel all of my skin off, well, problem. Probably not coming back from that one. This cell membrane is going to be kind of wavy like this, and what that does is increase the surface area. Because remember that the cell membrane's job is to allow stuff to pass back and forth, and the more surface area I have, the more able I'm going to be able to do that. It's going to govern things, and it's going to consist, oh my goodness, when we talk about the cell membrane, oftentimes we draw it, just like we just saw in the picture, like this. Like it's just a solid line, it's just a solid circle. This is not the cell membrane at all. The cell membrane is intensely complex. It is made up of protein, fats, cholesterol, and sugars. and it kind of moves in waves. It's like fluid, and it's constantly readjusting, and it's constantly changing shape, constant motion, really dynamic. It's an amazing, amazing thing. And this cell membrane consists also of a phospholipid bilayer. We talked about that in the last chapter. We had our hydrophilic heads facing the outside and our hydrophobic tails facing the inside. And we compared that to the buffalo. When a herd of buffalo are threatened, the ones that are strongest immediately form a circle with their heads facing out. The ones that are weakest are inside, facing the tails. The heads facing out of the buffalo circle love a fight. They are looking to protect, they are looking for a fight. The ones on the inside are the young and the weak and the sick, and they're terrified. They're not ready to fight. They don't want to have any part of this. So that's how I remember hydrophilic heads facing outside. The heads of the buffalo are loving a fight. The tails of the buffalo are where all of our frightened, young, phobic members of the herd are. So that's how I remember hydrophobic tails, hydrophilic heads. Love a fight, terrified of a fight. So there's our hydrophilic heads on the outside, hydrophobic tails on the inside. So there's my heads. Imagine here's my buffalo. Buffalo, they're in a circle. Here's my hydrophobic tails. And it's this philic and phobic that regulates what can go in and out of the cell. Fat-soluble molecules are going to pass relatively easily. Water-soluble molecules are going to have a little bit of a harder time because water and fat don't mix. Water can't pass through the hydrophobic, which is a lot larger surface area than the hydrophilic. So because our hydrophobic, you guys see hydrophilic, hydrophobic. So although the water would be able to negotiate just past the heads, we now have all of this stuff repelling water, and we really can't do that. Fats are able to use just a tiny bit of energy to get through, and then they are easily able to pass because this hydrophobic part of the cell membrane is made of fats. Fats love fats, and fats will allow fats to pass pretty much free. So if we have fat-soluble things trying to get in or out, we don't really have to use any energy. They just kind of let them have a free pass. If we have water-soluble, then we do need energy. Because if you've ever tried to wash a fatty pan with water, it doesn't work. And you're going to have to use a lot of elbow grease. Some other things that we have in this cell membrane, we have stuff called cholesterol. Now you've probably heard of this. Oh, I got to go get my cholesterol checked. There's good cholesterol and there's bad cholesterol. We're talking about the good kind. And this cholesterol wedges itself into the membrane, and it helps to have the cells be able to change their shapes. Our cells are really little shapeshifters. And depending on how dramatically they need to change their shape, that will determine how much cholesterol is found in the cell membrane. So oftentimes when we think about let's take a blood cell. Let's take a white blood cell, for example. We talk about our blood vessels and we kind of draw them like this, like a straw. That's not exactly how our blood vessels look. Our blood vessels are made with little spots, little spaces. So this would be one. We have the other side. And here is where my blood is flowing in the blood vessel. And what I need is for these blood cells to be able to change their shape and move through these little holes in our blood vessels and get into the tissue to do whatever battle they need to do with whatever foreign invader they need to do it with. And it's this cholesterol that help to stabilize the membrane and allow them to change their shape. Any questions? You guys are looking kind of dead-eyed. Do you really not have any questions? Or are you just like, oh, stop talking so I can go take a nap? You don't even have the energy to answer that one? Do we need to get up and do an interpretive dance? Get some blood flowing? You don't even have the energy to say no? Oh my goodness gracious, you guys.
Is there a dance for this lecture?
There could be. Like we could make an interpretive fluid mosaic dance. No. Mikhail's vote is no, but he doesn't even have enough energy to vocalize it. He's just sitting there going, just shaking his head. You poor thing. You poor sweethearts. You just, oh my goodness. Here is a picture of this cell membrane, and it really does show how complex. It is not just a line like this. This here is the cell membrane. Here we have our hydrophilic heads, hydrophobic tails. But we also have things like large carbohydrates. We have pores that allow bigger things to move back and forth without injuring our cell membrane. We have other kinds of proteins that help with the structure. And this whole thing is known as a fluid mosaic, meaning that it is in constant motion. It is constantly changing shape depending on the job that it's doing. So we have these proteins, these functional proteins, and they're responsible for our special functions of the cell membrane. So some cells may have more than others depending on the job they need to do. I'll give you guys a minute. When we start getting into the functionality of these cells, that's when the magic is really happening. That's where we start getting into how cells identify each other. Because obviously I anthropomorphize, but cells don't have eyeballs. They can't look at another cell and go, hey, you're a leukocyte, or you're an eosinophil, or you're a thrombocyte. You're okay to be here. They have other ways to identify each other. And when we start messing with that, OMG, then we got a whole heart of problems. Your immunity group is looking at this phospholipid bilayer and all of the characteristics, and it's also looking at the coating on this bilayer. Coating, I'm gonna say that right. I gotta Americanize that right up. The coating. Right. The coating of the cell is an identifier. Remember we said that we had some cells that walk around and they have a wanted poster for a foreign invader? And they're looking around and they're looking for this guy. Well, how do they identify him? It's because of the coating on their cell. Big problem though, what happens if your immune system stops being able to identify anybody? And he starts thinking that everybody's a foreign invader. He gets a wee bit paranoid. He thinks everyone's out to get him. He'll start killing off everybody. He just wipes it out. These are known as immunocompromised diseases. Like, I'll give you an example, lupus. Lupus is a disease where your immunity group stops being able to recognize itself and it starts attacking you. and it starts breaking you down because it no longer knows what is you and what is not you. That's a big problem. When your immune system turns on you, holy smokes, suddenly now your immune system has got the full force of the military attacking you as if you are made of Ebola. And then we got to do some stuff to calm him down. We give him some stuff so he just sits and pets the fuzzy wall. That's his immune system after. We're going to give him some drugs like steroid. That's what steroids do. Now immunity group, instead of like, kill everything, he's just like, whatever, somebody's going to pet this wall over here. I forgot to blink. And that's what he does. And all of that is due to this cell membrane, the cell's ability to identify each other. Now we have some cells that need to actively use energy, and this energy comes in the form of ATP. Somebody tell me what ATP stands for. Nice! I give you a unicorn high five. Adenosine triphosphate. What happens if I break a bond? I release something. I release energy. That's the whole point behind this. In this, that need this ATP, we break off a phosphorus, it releases a little lightning bolt of energy. Then we find a new one, we reassemble, break it again, reassemble, break it again, reassemble. And it's this breaking of the bond over and over that gives us this active energy. We also have certain channels that are found in the cell membrane. Now, all a channel is a fancy word for a door. It's something that allows stuff to go in, allows stuff to go out. This door right here, if we are on the inside of a cell, pretend this classroom now is the inside of a cell, and the walls are our cell membrane. We need to be able to leave if we have something important to do. This doorway is our channel. Now this doorway can be selective, where I say, okay, you know what, there's an emergency and we need to very slowly only allow certain people out. So this door is only gonna open for certain people. Or it could have something called a pore, where the door opens for all of you, and any one of you can walk through it at any time. So selective in my mind is like VIP status, right? It only allows certain molecules in and out of the cell. And then the pore is going to allow free passage as long as you're supposed to be there, right? You all can walk out that door, you can all walk back in that door. Well, right now, any other cohort, my onyx, my sterlings, my rubies, they're not allowed in that door. And so that would be a selective. Only the royals can go in and out. However, because any royal can go in and out, for you guys, it's considered a pore. Allows you guys to travel back and forth freely, but it is also selective because it keeps everybody else who's not a royal in this class out there. Does that make sense to everybody? Arms are so dry right now. I need to put some lotion on it. Cell membrane is dry. Look at that. Isn't that gorgeous? Just look and look. Just admire the splendor for a minute. You guys are not appreciating this. You guys are really not appreciating this. This is art. Look at how complex that is. That's a one tiny sliver of one cell membrane. And every cell in your body has got something similar to this. That's insane. That blows my mind. That blows my mind. Here we can see we have carbohydrates, which are sugars. There's our cholesterol, which is forming the structure and allowing the cell to change shape. We have these embedded proteins, which are also helping with the structure. We're going to have pores. I don't have a pore on this one, but we have pores that allow larger molecules to pass back and forth without destroying this very delicate phospholipid bilayer. This is amazing, guys. You better not. Fine, I'll appreciate it. You guys just are not. So we have some proteins called peripheral proteins. Now tell me what the word peripheral means. If you see something out of your peripheral vision, where is it? It's out here to the side. That's what we're talking about. Peripheral means out to the side, away from the center. And these peripheral proteins, here is one here, peripheral, and these are also involved in helping to change the cell's shape. You got an awful lot of things that help to change the shape of these cells without destroying it. And these peripheral proteins are part of that. That's it. That's it. Give you guys a minute. Hey, what's the hard outer surface of the bone called? This is our compact bone. What is the inner sponge toffee called? Cancelated, cancellous. What are the ends of the bone, ends of the long bones called? You got it. No, you got it. It's just your pronunciation, the epiphysis. No. Epiphysis. What about the shaft of the bone? Yes, the middle, this shaft of the bone is called the, starts with a D. Diaphysis. This is a femur. Just for your own information, this is a femur of a cow. This used to be your live cow. This is a real bone. All right, so remember how I said that cells need to be able to recognize each other? Well, obviously they don't have facial features, right? They don't have eyes. They can't like look out and go, oh, okay, you know, I recognize who you are. Our cells are going to use a coating, a very special, gotta Americanize that coating. It's the coating of the cell. I don't know why my American is this horrible Texas person. This is a glyco, meaning sugar, calyx, meaning coating or covering. This is how cells identify each other. They have this sticky coating on the cell, and when they come in contact with another cell's coating, it's almost like a blind person reading your face. They're able to read this coating, and they're able to identify who is supposed to be there and who is not. These coatings are unique to every cell. And the other thing that they do is they help to provide adhesion. So what is adhesion? Let's do an easy question. What is it to adhese something? Stick it.
Together.
Why do cells need to stick together? That's weird. We got a couple of reasons. I'll give you a few examples. Let's say you're a foreign invader and you're trying to get into the body. And I have now located you and I'm like, stranger danger, stranger danger. The first thing your white blood cells are gonna do is they're gonna essentially, in my mind, they're linking arms and they're forming a wall. And they're saying, you can't come in here. We will physically stop you. We will physically stop you. Well, they don't have little hands. They can't link their little arms. Excuse me, invisible bug. What they can do is wrinkle up against their glycocalyx, stick together. Another reason why they might momentarily need to stick together, let's say I am a cell and I'm trying to get to that door, and there's only this one little tightrope that I can use to get to the door. But coming the other way is a cell that's trying to get over there. There's only this one little tightrope to do it. How do I continue and how do they continue? Well, what we can do is stick together and then roll over each other and continue on our way. That is our glycocalyx. So this is how we identify cells, viruses, because every cell, including bacteria and viruses, have this identifier. So when we're using our mental image of the little private investigator with the wanted poster, what we're actually looking at is a type of cell, a type of antibody that goes around and basically touches everybody, trying to find this unique identifier for the foreign invader they are programmed to go find. The big problem right now with the foreign invader we're all dealing with right now, stupid COVID. COVID's actually really, really smart and really, without it being a pandemic and killing a crap ton of people, he's actually really elegant and really terrifying. Because the minute that our body goes, okay, I got the wanted poster, goes around, tries to find him, he changes the sugar coating so that the wanted poster doesn't match anymore. Yeah, and I know. And he's evolving and changing in the blink of an eye. And so then he just goes, whoop, and he changes. And now I've got all these wanted posters, but they're not identifying the right guy. And so that's how he can get and reinfect you as if you've never been infected before. The whole idea of antibodies is to help immunity group figure out what battle style to use. The problem is the battle style that I have programmed for COVID changed, and my body doesn't even recognize that it's him. That's terrifying. That is absolutely petrifying to me. That in the span of 4 months, 5 months, he has mutated somewhere around that we know of 4 to 6 times in a matter of months. How is that not mind-blowing to you? You guys are hopeless today. You are hopeless today. Tomorrow we're coming with a little bit more energy, or I am going to make you dance. Fair warning. All right, so we're gonna pick it up here on tomorrow. You guys have a most fabulous day. You guys in TV land, we'll pick it up here on tomorrow, and I'll get you your catalogs on Wednesday. Have a great day, guys.